Um, Hello, everyone. I'm Jeff Carlin, and my colleague Yumi Choi we're gonna sort of tag team presenting you today. Um, uh, Basically, giving you a quick rundown of the tools that are available to you to access Data Preview 0 currently, and they are the same tools that you'll use to access LSST data in the future. So I these slides have a few links in them that are very handy. So I just pasted a link to the slide deck in the meeting chat. So I could show this. So Yumi and I are here on behalf of the Rubin Community Science Team. It's a team that has been growing quite a bit recently and is still growing. And our purpose is to facilitate and enable science by the community. So we include people who are representatives or members of all of the various science collaborations, a wide range of interests and expertise represented on this team. So Yumi and I are both Rubin community scientists, along with all of these other people you see here. And so you are welcome and encouraged to reach out to any of us anytime you have questions about Rubin data or data access or the survey. Okay, and this is the slide that I was mentioning that has a bunch of links to resources that will be really handy for people. And actually, we'll actually visit some of these places. One place that could be extremely helpful is the community forum. This is our forum, sort of think of it as, I don't know, Stack Overflow or something, as the place for you to go and have discussions, ask questions. You can get support from people on the project as well as just discuss with the community science or data handling issues. And so this is the community forum. Anybody is welcome to sign up for an account and use the forum. So do feel welcome to do so. And you can see it just as you have a bunch of topics, including support topics related to the science platform, Data Preview 0, other such things, and science topics as well. And then you can just see an example here of the stream of posts that have come in recently. Another link that you may need right now to follow along is the link to the Rubin Science platform. And this is we'll be demonstrating to you, and this is your means of accessing data. So because of course, LSST data is just there's gonna be such a data volume that you won't be typically able to download data to your local computer and work on it. So the Rubin Science platform is a resource hosted on the same servers that host the data. So you can work next to the data. And as you'll see, it's most of the programmatic access to data is via the Python Jupyter notebooks, and we'll also show you the portals. So, that link is provided here if you want to follow along with our demo today. We also, excuse me, I also put a link here to the Data Preview 0 website, which has a lot of information about the data set itself, but also links to a lot of tutorials and sort of I don't know, documents to help you get started with the Data Preview 0 data set. So I encourage you to check this out if you are interested. We also have all of the tutorials that we produce as the community science team are available in this GitHub organization. And I also wanted to highlight that not only are the tutorial notebooks available, but we also have enable DP0 delegates, people who have signed up and have our access to the science platform. We provide a space here where people can share the notebooks that they have produced for their science explorations. And so there are a lot of resources here that you can access, and you can contribute if you are so inclined. So we will be demonstrating accessing the data preview 0 data set today, which is based on the Dark Energy Science Collaboration's Data Challenge 2 simulations. So this is a completely simulated data set with sort of model Milky Way, and you'll see it's for people who are Milky Way scientists, you might find that it does not look like the Milky Way that you know and love, but it is a it is a reasonable simulation for getting started, you know, getting used to the tools. And so with that, I think I will turn over to Yumi, who's going to actually start us off with a science platform demo. And we are both available. You can send questions via chat or on the Slack. Feel free to jump in at any moment.
Okay, thank you, Jeff. Does everyone sees my Jupyter Notebook page? Okay, cool. Yeah, thank you. So I'm Yumi Choi. I'm a part of member of the Rubin Community Science team. Before getting started, disclaimer first. So Jeff and I prepared 2 little demos for today, and we tried to tailor our little demos for this particular workshop, but we're not Ultracool Dwarf people, so please keep that in mind. And our demos will cover the notebook aspect of the Rubin Science platform, as well as the portal aspect. And Jeff and I will take turns to run our demos, which might be hopefully more fun. Okay, so let's start with the first one, which the title is, the name of the notebook is Cool Dwarfs underscore CMD underscore CCD. So, and all the Rubin Science Platform tutorials, notebook tutorials or portal tutorials start with the basic information at the beginning, including a brief description and goals of the tutorial. So here, our goal is create point source color magnitude diagrams and color diagrams, and eventually select the Ultracool Dwarfs. So with that, we first import all the modules, packages, modules, the functions you need. So for this particular notebook, we're importing a plotting module and a tab service function used in this notebook. And then we instantiate the tab service. Tab stands for the table access protocol, which allows you to execute your ADQL query and retrieve the result. The ADQL, for the people who's not familiar with, stands for astronomical data query language. And then, unless you're interested in the solar system object, DP 0.2 might be the main schema you want to explore before any type of real data that the LSST will deliver. So let's explore the DP 0.2 schema, and this query is to, oh, by the way, is the font size okay? Maybe this might be better. Okay. This query selects all the tables available in the DP 0.2 schema. There are 11 tables, and you can see the descriptions for each table. And among 11 tables, we're gonna focus on the object table here for this notebook. And this object table contains the properties of the astronomical object detected and measured on the deep co-edited images. So in the next cell, let's get all the information about the columns available in the object table. And you can see there are 990 columns in this table, which is a lot. So they are hidden. Only the first and the last portion of the table is displayed by default. But you may want to see all of the columns in the table. And if you want to look at what kind of columns available, then uncomment this cell, and then you can execute, and that will show all the 990 columns in this table. It's very long, so I'm gonna comment out this. And then we just, one good behavior working on the RSP is clean up any query results that you're not going to use in the following analysis anymore. Just delete and then clean up, so that way you can hit your memory capacity. Okay, so let me execute this cell first and then explain what they are doing because the querying data takes some time. So here, this query, we're querying GRIZY AB magnitudes for point-like sources by requiring the extendedness parameter to be 0 that have no children by requiring the detect underscore is parameter primary parameter to be 1, and then have the signal to noise ratio greater than 5 in IZY bands in a 2-degree radius region centered at RA of 55.75 and declination of minus 32.27. Okay, so we got the query. And again, we can uncomment and see the table, the result table. So it has GRIZY columns for the 72,000, about 72,000 objects. Okay. And then let me, so now, okay. So now we create the color magnitude diagram and color diagrams from the result table. So here we can make plots for the I versus G minus I color and I versus the I minus Z color. And this is the CMDs. Maybe it's different from what you are seeing from the real data. So this is the simulated data. And then the really quantized features in the red colors are coming from the procedures that how data challenge to simulate the stellar object in the Milky Way. So this is kind of artifact. And then we can also create the color diagrams, various color diagrams. using the same result table. So here, I minus I, G minus R minus C versus G minus R, Z minus Y versus I minus G, Z. So you probably see to the Ultracool Dwarf experts, you might able to spot where you want to select the star or substellar object. And here we are trying to identify ultracool dwarfs, probably like late M or L and T dwarfs. So we selecting objects that have the I minus Z color greater than 1 and the Z minus Y color greater than 0.6, which we kind of, that's our rough choice. And then we overplot those selected cool dwarfs candidates on the same CMDs we plotted above. They are located in this part of the CMDs. Okay, so any questions before Jeff talks about the portal aspect of this notebook content? Or we have like 10-minute discussion time after our tutorial, so we can take questions then too. If not, I'm gonna stop sharing and Jeff, take it over.
Yeah, and we purposely kept the demos short and simple so that there's plenty of time for questions and discussion. So if you have any questions, don't be shy.
So I'll ask the question now. These are all like what I say, regular magnitudes, like base 10. There's none of this weird SDSS, you know, hyperbolic sign, Lupton magnitudes, or
no,
So
these
it's
are. Oh, go ahead.
Yeah, these are the standard AB magnitude.
Great.
Yeah, and in fact, excuse me. In fact, you can see in the cell where we actually did the tap query, we applied this built-in function to actually convert, because they're reported as fluxes in the table, and so this converts those fluxes into AB mags here. So those are actually in the table. They're stored as flux in nanojanskis. Oh, you can. Sorry for the dissonance here. I prefer the dark mode. This is the same science platform that Yumi was showing, but I just have it in dark mode. So you can see at the bottom of the notebook, we have this section. We're going to repeat the same activity, or the same activity anyway, in the portal aspect. So this was all, this is a Jupyter notebook executing Python commands to do the plotting and everything. But that's not the only way to access data. So we want to show you how to do this via the portal aspect. So again, you go to data.lsst.cloud to access the portal. So to get to the notebook aspect, you click on the part that says notebooks. That will take you to something that looks like this. But if you instead click on this box, it will take you to what's known as the portal. And so this is a way to query and then manipulate the returned data tables. And so you can see here that this has the data preview 0.2 catalogs. You can also see that you can do other queries, but we're going to stick to the data preview 0.2, DP 0.2. And here you can see those same 11 tables that were listed in the notebook demonstration. So there's there are the object table, which is measurements from the coads, the deep co-added images. The source table is all of the single epoch measurements, which you'll see more of in the second little demo that we're going to do. Forced sources are forced measurements on all the single epoch images based on the positions found from the object table. And then you have difference image measurements on difference images where each image has a template subtracted to look for transients and variables. And then you have some tables that give you some summary data about the visits, for example. So we are going to stick with querying the object table. So you can see you can enter, for example, you can enter a spatial query over here, and you can see that when the table is highlighted, that you can select which columns you would like it to return. So you can do your queries that way by, for example, I'll just demonstrate here. Let's say we'll do at that position 10 arcsecond query, and let's say, I don't know, we'll say just return all of those columns just for fun. We'll see what that does. And then you wait patiently. Okay, I did not expect it to take that long. There you go. So there you can see you've returned 37 results in that 10 arcsecond query. That's not, I just wanted to show you how that works, but then you can see, you can tell it to populate and edit the ADQL, so then you can actually manipulate the tap query here. So this is the same query, but now this is showing you what actually happened under the hood. And so then if you wanted to, apply some constraints or something, you can do that here. So where'd we go? But instead of, if you don't just want to, enter a query here and then populate the ADQL, you can just go here directly at the upper right where it says edit ADQL. You can go there and, oops, and actually, I shouldn't have done it with that ugly query. It's long. Here. So you can go via that button at the upper right to edit ADQL, and this gives you the box where you can type the text of your query. And you can see there are sample queries given as examples here. But we're just going to copy and paste the query from this demo notebook. So you can just copy this and paste it directly into this box. And you can see this is the exact same query that that Yumi showed us before. We're doing a 2 arcsecond radius, picking things that are not extended, signal noise greater than 5. And so once you've pasted that in, you can just we'll increase this because remember it returned 72,000 results. So we'll set the row limit to 75,000. And then we just click search, and this might take a second. Oh, I see Bob's question. If you go to the slides I can share that link again. For those who were not here at the very beginning. So here's a link to the slides that we showed before, but you can see there's a link to our GitHub organization, which will take you to this page. And the two demos that we're doing today are in this repository called Little Demos. So so you have access to those in this Little Demos repository. Okay, so while I was chatting, our query completed, and you can see we have 72,662 results returned. And you can see that we have the magnitudes in the GR-IZY bands, just as we did when we did the query from the notebook. It, by default, will bring up a plot showing just the first two columns. So this is handy if your first two columns are RA-DEC, for example. You'll get a plot showing you the positions of your query results. G versus R is maybe not the most exciting thing for us, so let's try changing that and plotting a color magnitude diagram. And so the way you can edit the chart that appears here is by clicking the icon that looks like two gears interlocking. You can see when you mouse over it, it tells you what that tool does. So if the icons don't read as obvious to you, then you can always mouse over and it'll tell you what that tool does. So here we're going to go into the chart options, and that will pop up this parameters window. And now you can see that you can change the columns that are being plotted. And for example, since this is a heat map, you can change the number of bins in it. So let's plot a color magnitude diagram. So we can go I mag minus Z mag, and you can see it also will autocomplete your if I type I, it brings up any columns from the table that start with the I. So it brings up I mag right there, and I can just click that or type it completely. Let's try a different color scale just for fun. So you can see by default it's just a grayscale. I don't know, we'll try, how about a picnic? I don't even know what picnic looks like. We'll find out. And 100 bins in each axis. And then you can see if you click on this arrow by the chart options, I can edit things like the title. I'm going to not enter the labels here because it'll by default just put the column names. But you can see another thing that we want to do for color magnitude diagram is we want to reverse the y-axis. So you have that option just by clicking this little radio button here. And you can set the plot boundaries, for example, and other options. So let's click apply, and we'll see what that does. And now I know what a picnic looks like in color scale. But you can see we have our color magnitude diagram, the same as we had before. There's a large concentration of objects here, which are, nearby FGK dwarf stars in the Milky Way disk. And then you see those vertical stripes of the quantized colors of ML and T dwarfs in the catalog. I think we'll stop there for this particular demo, but that just shows you how you can do the same actions in the portal or the notebook. And before we go on, If anyone has any questions, happy to address those. Let me see if there's anything in Slack too. Okay, well, feel free to pop in anytime if you have questions. The other demo that we were going to do is a brief demonstration of how to extract a light curve. You'll see that there's not there are variable stars in the simulated data set. There are Lyrae stars and Cepheid variables. There is a category of simulated stars that are MLT dwarfs that are given some variability, but it's really usually really low level variability. So we may or may not see anything interesting in the light curve, but you'll know how to extract a light curve once you've seen this. So we again are going to use the TAP service to query the database. And this is just setting up some plot defaults so that it'll look nice. So here we initialize the TAP service. And so we're going to do the same query that we did before from the object table. We're just going to select I, Z, and Y band mags now, again, in a 2-degree radius. And you can see here we're applying those color cuts to select things with I minus Z colors larger than 1 and Z minus Y greater than 0.6. This will take a second, so let's get it started. And we're going to then use the results of this to pick one of the objects that's returned to then go and grab its individual measurements from all of the visits. So this might take a minute. So while that executes, we will move ahead a little bit. And we're just going to sort them by magnitude to grab the brightest objects, because we didn't apply any magnitude cuts here. So of course, a lot of these are going to be way down by the mag limit. So we're just going to do a quick sort to make it easy to grab the brightest objects, so we can get a nice looking light curve once this completes.
So Jeff, this is all, they're like simulated images, and then the data pipeline ran on them. And so this is all kind of things that would really be measured. Like there really will be an extendedness equals 0 flag, and that will be how we, select point. And then I guess we could look somewhere, eventually, we'd want to look under the hood and find out how that's determined, right? And how accurate it is or something, but
Yeah.
but to start with, that's the kind of thing we'll really see.
Yeah, this is yeah, there's simulated images, and then the pipelines were executed to create these catalogs. And so that reminds me also that another way that you can Yumi showed how to print the list of columns from the notebook aspect. Another quick way of seeing what columns each table contains is to just go to the portal, and you can see here that in the list of columns, you can see it actually has the column descriptions. So that can be helpful as well. And as Aaron just noted, we also have the schema online on the DP0 website. Okay, so we returned some objects. We have 370 objects meeting our criteria, and you can see they're sorted by Z magnitude. So it's ascending here. So we'll just take the brightest one first and see what that looks like. And so we will use the object ID of this object as the key to query the source table. So this is the object, the identifier for this particular object. We just say select this object. It's the first one, so index 0, select that object ID. And so now we're querying the forced source measurements. So these are taking the position of this object and going to every image, every individual image, and forcing measurements on each image. And so here you can see we'll return, it will return data from all of the bands, and we will extract the fluxes, we'll convert them to magnitudes and magnitude errors, and we'll get some information about the time that each exposure was taken. So this is the exposure midpoint in MJD. So we'll need that if we want to plot a light curve. And so that requires you to do some joining between that forced source table and the visit info table so that you can extract that time information. And you can see we then select signal to noise greater than 5 detection or measurements in I, Z, and Y band. So we'll execute this query. I should have executed it before. So this returned all of the measurements for that one object. And so here you can see what that looks like. You can see that we have 250 measurements, I guess, at signal to noise greater than 5 of this object. And you can see here as well that it has the measurements in I, Z, and Y bands. So you can pick those out using this band column. Excuse me. So basically we're going to do that here. We're going to loop over the 3 different bands, the I, Z, and Y bands, and we're going to extract the measurements and plot time on the x-axis and magnitude on the y-axis to show you a light curve in each of the 3 bands. So you can see here, this is magnitude, and this, there, it's the MJD of the measurement, and in the 3 different bands, the I, Z, and Y band. So it's maybe not, this is maybe not the most useful scientific presentation right here. So let's instead go look at each of them with the mean magnitude subtracted off, so we can see how they vary relative to that mean magnitude. And this cell is just setting the minimum and maximum time, extracting that from the table. And then here we'll plot, this is each individual measurement minus the mean of all of them. So it should be focused around 0. And now you can see real variability happening here, or what looks like real variability. And in fact, and as Yumi pointed out, and I'm not an expert, but if I had to guess whether there was a flare here or something, I'd say possibly, but y'all are more expert than I am about cool dwarf flares. But this, you can see some variability in both the Z and Y bands of, 1/10 of a magnitude or something. So I will not interpret that any further, but that's an example of what of how you can extract and plot a light curve in all 3 bands. And then I'm going to pass it to Yumi to show you how to do the same thing in the portal aspect. But before if anyone has any questions before Yumi takes over.
I'll go ahead. So of course, I understand DP0 doesn't include like astrometry variations and things like that, but in principle, if someone was trying to do, get the position measurements, for something that they think is an astrometric binary or something like that, they would basically be doing the same thing as here, right? There would be some sort of centroid column, I guess, of some sort, and they could get that out, right?
Yeah, in fact, we've extracted the position, I think, when we did this. Yeah, we did extract the positions, but yeah,
Oh, I see. Yeah.
as you mentioned, that there's no astrometric variation in the simulated data set. But yeah, you could you're exactly right. You could just do the exact same thing and just plot a time series of the
Cool.
the position measurements.
I would think that perhaps that would be better done with the source table rather than the force source table, because it's not entirely clear to me whether the force source is taking into account centroid motion. And early in the survey, I don't think you'll have well measured proper motions to force on anyway.
Yeah, absolutely right. I would definitely use the source table for that and not the force source measurements. Okay.
Okay, thank you. Okay, so the portal aspect of this notebook was originally just described for plotting the light curves, but because we have more time, I think I can do the first queries as well. So here, first I go to the data.sst.cloud and enter the portal aspect and click the edit ADQL tab, and I'm gonna copy this query, the first one, not the first one, this is the first one. Okay. So select all the NLT dwarf candidates. Right, so I'm copy here, and I think the notebook, we sort by Z magnitude after retrieving the data. Maybe we can do in the query here, maybe Z mag and search. So in this query, let me execute some. And the brightest one, the source object ID was this. So we just want to make sure that we get the same sorting by this query. And it takes some time. I just want to inform you that even with this really the exact same queries, depending on the day and time, the RSP's responding time might be really different, depending on how many resources are used at the same time by how many people. So. And then also want to mention that that compared to the Jupyter Notebook, the portal aspect provide a limited capabilities in terms of coding or doing any fancy stuff. So you can consider the portal aspect as a initial analysis or to get some ideas of the tables and data sets. So exploratory things analysis, and then you can move on to the Jupyter Notebook aspect and do more in-depth analysis there for your data. I think this takes longer than should be. The same for Jeff from your side.
I was just going to try it, see if it would execute faster for me.
Okay. If that takes too long, we can just do the liker part. But I just want to show. Okay, maybe we can just cancel that and then copy this query, which is retrieving the IZY band measurements for a specific object. And then we are gonna plot the light curves as Jeff showed. So just cancel it. And just go back to the query and then search. Okay, so now it worked. So we got 250 measurement, which is the same number that Jeff got for this particular object. And as you can see, the position on the sky is just a single dot because there's no proper-motion or parallax measurements available in the simulated data. So if we maybe here, oh no, this is just make sure that we got all the object have the object ID, the same object ID for 250 measurements, and that's right. And so you go to the active chart portion of the layout and then click the 2 gears icon and then modify the trace. So here we're gonna use the midpoint MJD. So if you start typing EX, then it gives the column. And then here we're gonna PSF magnitude, and then also overplot the PSF magnitude errors. And then tracers here, the photo aspect is cannot loop through the filters. So you have to come up with a way to differentiate the measurement in different colors, different filters. So here we're gonna use the 0 point information, which should be really kind of different for each filter. The 0 point is for each CCD, each visit level, what should be the 0 point in the each measurement in each filter. So you is that IZY filter should have different 0 point. And so we're going to use the 0 point magnitude as our color map, and then I will try the rainbow colors and reverse the white level to plot the brighter magnitude in the upper direction. Okay, so here these are the one filter, and then these for the another filter, and then these are the third filter. So I think as you can see, there is a highlighted raw, which is this data points, and this is in the Y band. So this is the Y band like curves. If you click through the different rows, then you can see the dots in the plot here is changing, right? And then if we click the object in I-band, then it's highlighted where? Oh, here, down here. So orange dots are showing the object you're clicking in the table. So this is the I-band, like curves. And then the ones in the green squares, green dots are the measurements in the G-band, Z-band. And you can click through the filters. Or you can also order by filter by clicking just the columns. If you want to order this table by CCD visit ID, then you just click it and then it will order sort the table using the CCD visit ID or magnitude or band, whatever columns you want to use for sorting. And then maybe I can show one more aspect in the portal aspect. So you can actually add columns here after calculating something. So maybe I don't want to say, okay, I want to plot the I minus Z color every time by saying I mag minus Z mag. So I can define color IZ and then expression I mag minus Z mag. Okay, and then add column. Oh. No.
Since this is the source table measurements, that we don't have the IMAG and ZMAG as separate columns.
Right. That's right. Okay, yeah, but in the object table, you can do that for the color. But here, you can do whatever calculations and then add as an extra column in the table. And then save your files, the table, then download to your local computer. So yeah, here, as I mentioned, the portal has a limited capability than the Jupyter Notebook, so we don't plot the medium magnitude subtracted light curves, which shows the variability more clearly. But can make a initial analysis for these.
One thing that is nice about the portal, though, is that for exploration, as Yumi was saying, like you can do a lot more interactive sort of exploratory stuff and sort of hone your queries, and then if you want to go to the notebook aspect for deeper analysis, it's really handy for that kind of work. You can see that you can interact with the plots.
Yep.
And you can filter on the columns from the table, for example. So if you wanted to only plot the I-band, for example, yeah, you could just type equals I and everything disappears.
Nice. Oh, yeah, you made a zoom plot, so that's why. Yep. Anyway, so yeah, you can filter out, apply the criteria in that way. Okay, maybe I can stop sharing here and we can take questions.
That was just some really basic introductions to the capabilities. Of course, there's a lot more that you can do, and so I encourage you all to, if you're interested, you can register for an account, and as long as you are a data rights holder, you can register for an account and play around with. We have a lot of tutorials and a lot of demos that you can go through on your own time.
No, that was great and really informative. Every time the great thing about seeing this is it suddenly made me you realize how many questions you have. You're like, oh well, how is aperture flux calculated? And you realize you have to, there'll be a lot of documentation, of course.
Yeah, Aaron Meisner is one of our documentation specialists within the community science team. So
Yeah, I would just
Yeah.
say with the example question John raised there, there's something that Rubin has, a formal project document called the Data Products Definition Document, DPDD. And so I would recommend looking at that for what the actual formats and methodologies would be for real data releases of LSST, which are very similar to what's been shown here, but may have slight differences. And then failing the DPDD, the next step I would recommend taking would be sort of search terms on the forum to see if it's a question that's been asked already. And then if not, feel free to ask it on the forum if it's like a technical question, like the one that came up about, are proper motions taken into account in the force photometry in some way? So that would be my recommendation of how to go about trying to get questions answered.
And for those watching the recording, it turns out there's a very simple link to get to the document. It's ls.st/dpdd to get to the DPDD document. And I know that SRD also works for science requirements document. Now I'm willing to extrapolate to many other documents. Are there other questions? Wei Chun?
Yes, thank you. Thanks for introducing this fantastic software. It's really powerful. Just quick question here. Will LSST consider to include the magnitudes in the final data release? So instead of calling that little functions every time to convert nanojansky to magnitudes, is there any reason why not include the magnitudes in the table?
I think that the tables will always contain fluxes. And so I think the answer is no, we probably won't ever serve magnitude columns in the tables. And I think it's in part so that the science user can make their own choice. If you want AB mags or Vega mags or whatever, you have the flux, you can transform it however you wish. But I agree that it is kind of an extra step that it would be nice to not have to do. But I think the answer is it's almost certainly going to be reported in flux only.
Thank you. One more question. Sorry. So will the LSST work with the TopCat group in Europe? So the TopCat can also access the LSST.
Yeah, in fact, you can access the data preview 0 data from TopCat right now. You may have seen when we went to the login page for data.lsst.cloud, it had the portal aspect, the notebook aspect, had on the right API aspect, and that is referring to exactly what you're asking about. You can use standard, it's all IVOA compliant, all of our tools, so that you can, from TopCat, for example, you can query the data set. And so there is a demo. There's a video of when Douglas did that demo, right? Yeah, so there is a demo available on if you go to the DP 0.2 webpage, you'll find a video of demonstrating how to do that from TopCat.
Thank you.
I also wanted to add that there is in the little demos repo, there is another notebook that's showing API from NOAA Lab. NOAA Lab, Astrodata Lab, you can also access the Rubin data. So you can follow that if you want to check it out.
I guess a related question, well, not related at all. So this was sort of all implicitly sort of through Noir Lab. Is it right that there are going to be mirror archives or alternative ones in some international partners? As that was a contribution that was made. I don't know what the status of that is. I only remember having to read proposals once.
Yeah, there will be what are they called? But there will be other instances of the science platform at international data centers. But they and I think that it's sort of up to each of those data centers to choose how they deploy things. So it may not be the exact same science platform, but there will be similar tools, I think, elsewhere. Yeah.
Dave Monet had his hand raised, at least briefly.
Sorry, can you hear me now?
Yes.
Hello?
Yes, we can hear you.
Yeah, I guess one of my concerns is it seems that all of the demonstrations that the very that I've seen on how to use all of this stuff, that astrometry is always shuffled to the future indefinite tense, and we're not that far away from wanting to or actually getting stars that will have proper motion and parallax, and how the deep coads will happen, and how all the general astrometric strategy, I guess, always seems to be delayed. And I'm wondering if is work happening in this area? I'm not going to press for answers. I was just curious. My concern is that it would be nice to start practicing on astrometry, with astrometric parameters somewhat before we actually have the real science data. Thanks. Over.
Yeah, thanks, Dave. The answer is that there is work happening. Things are being implemented in the pipelines, and so definitely by the next data preview, which will consist of on-sky data from commissioning, that will contain. I guess I can't guarantee that it'll contain a full 5-parameter solution or for every object or not, but it will contain a more, let's say, up-to-date version of what our pipelines measure and produce.
And I guess speaking of sort of future work or ongoing work reminded me that over the years, there's been a lot of talk of a special sort of crowded field pipeline, which, is obviously very important to stars, Milky Way, local volume and all that. Will that appear like as just totally separate columns, or will that sometimes be run and there's a choice being made? I remember that there were many, many options that the project or DM was considering. How do we find out, what's going to happen?
Yeah, I actually don't know that there are definite plans yet. So yeah, so it's a very good question. And I think I would have to ask around to find out. But I think the answer is probably that that we're just not sure yet how we're going to provide that. And it's likely that it'll be something that might be contributed by an in-kind contributing team or something. So I think that the details maybe are not decided yet.
I know that there are people working on it, but I think we have to ask often.
Most of the algorithmic development work is going on with the Princeton group. And so I think this is a good case where if you asked it on the forum, that would prompt someone from that group to tell you what the latest, greatest status is. I mean, there's weekly and even daily releases of the pipeline. So I think this is a case where you would want to ask on the forum and find out what really is happening in closer to real time.
Maybe might be a good topic for someone to remember to bring up for whatever the annual community, whatever the new name is for the community workshop in August. Maybe we can get a session on it or something.
Or perhaps go to someone on the users committee and ask them to raise it in one of the users committee meetings, for
Yeah.
example. Although to be honest, I think the forum is a better way to go for this. Otherwise, you're waiting for every 6 months for the users committee meeting.
Yeah, I know. For context, obviously the default pipeline, is meant for the high, the high latitude, low extinction sky where everything is a galaxy. And of course, if you observe in Bade's window, then everything is a star, right? And there's a star on every pixel. And so you sort of, there are sort of well-known sort of solutions or algorithms that the community, I think, accepts. It's just a matter that they have to be implemented in some way. So this has been an ongoing topic of discussion for many years.
There is a subsection of the DPDD 4.2.5 called crowded field photometry. I can't say I have it memorized by heart, but it might be worth looking at that.
Yeah, I mean, I think a decision was made to go forward with it, so to speak. So it must, be appearing in documents at some level. I mean, that's just outsider, little flippant, sorry. Are there other questions? Kelly Cruz will be next, but on the regular schedule, we have 5 minutes, and maybe everyone would like to take a breather. Or we could have more questions. Kelly, are you happy with starting in 5 minutes?
Yeah, I would prefer 5 minutes so I could do a tech check.
Excellent. So let's I'm going to pause the recording now, and we'll take a 5-minute break or 4-minute break. Okay, we're back.
All right, hi everybody. My name is Kelly Cruz. I know most of you, and also from looking at the participant list, I think for most of you, I've actually talked to you individually about the simple archive. So I'm really happy to have an opportunity to talk about it more. Right, so I'm Kelly Cruz. I'm a professor at Hunter College. I'm based in New York City. And I'm super excited to talk to you today about the Simple Archive. So the Simple Archive is a database. So it's not, so we're going to talk about the Ultracool sheet next. And so one of the big differences between Simple and the Ultracool sheet is that the Simple Archive is a database. You can interact with it in multiple different ways, and I'm going to show you a lot of the features today. But first I wanted to talk about completeness. And let's see, I want to go to about. And so we have over, what did it say? I think, are we at 3,900 now? Okay, we're at about 3,500 sources. We just did a cross match with the Ultracool sheet, and we have 3,000 sources in common with the Ultracool sheet. 860 of the sources in the Ultracool sheet are not in Simple. And that also means that there are probably 400 sources that are in Simple that are not in the Ultracool sheet. My goal is about functionality and like user interface. My primary goal is not necessarily completeness. And so that's one of the things I really want to talk to this audience about is to convey that really the goal is for this to be a community resource and a community maintained archive. Like, we can help you ingest the data, but we need the community to be able to tell us, like, oh, this is the data that's missing, or this is the data that needs to come in. And so I will show you that in a second, but I did just want to show we have in the about page, we have some figures just showing you, giving you a graphical representation. So over on the right is the counts versus spectral type. So it's low mass stars, really starting with like the Ultracool Dwarfs, around M7, all the way through the Y dwarf sequence. And then we also, in scope, are directly imaged exoplanets. So we have like VHS 1256b and things like that. I have my notes keeps. All right, right. So I want to use my favorite source as an example. So I think the website is one way to interact with the archive. It is probably going to be one of the most common ways, but it's really the way you want to see if you just want to like look for an individual object. If you want to look for a individual object, the website is a good place to start. So I want to look for 2MeS 0355. Notice that it auto completes, which is really, really nice on the sources. So I could also type for like TWA and I can see those sources. I can search for VHS. I can search for SIMP. So the search for an object toolbar is already a really helpful place to start. And so let's look at the individual source for 0355 plus 11. So that was just a shortcut for doing a whole search. It now shows me the results. And then I can click on it and it's now loading all of the holdings for this individual source. It's going to take a second. Right. And so now you can see all the holdings. So here's it is an entry in the sources table. It has an RA, a DEC, it has a short name. It is known by many other names. We don't try to duplicate information that is in Simbad, but when we do ingestion, if someone has called it something, we try to keep track of it so that it will turn up in searches if you search for things that have other names. Right, it has a little I forget what this thing is called, Aladdin viewer. All the photometry points that we know about. There's an interactive color magnitude diagram. This is a place that I think could use a little bit of improvement. So it's actually, you can change the X and Y axis to all the combinations of the photometry. It's a little bit unwieldy, but there's potential there for seeing where the object lies on the color magnitude diagram. And I think, yeah, you can hover over these to see what the other sources are in the database that also have Sloan I and Ys. Spectra, I think, is one of the most useful things. So here's all the spectra that we've ingested on this particular source. Let me move my things over so I can. If you wanted to download all the spectra, you can click the download button, and I'm pretty sure that gives you a tarball, or you can download individual ones by clicking on the link here. These are in, as many of us are familiar with, we astronomers write spectra in many different formats, which with my AstroPi hat on, I'm trying to improve that situation, but we have a large legacy of spectra in many different formats. Of the spectra that are stored, that are easily readable by specutils, by AstroPi specutils, we have them plotted here. You can turn them on and off by clicking up here. And you can, this is a bokeh viewer. So one of the things I always like to do, you can just draw a box. That's the default. You can draw a box and then there's a normalization slider. And so you can do quick look spectra. This is not designed to, measure equivalent widths or to do analysis. This is just designed to do quick look of the spectra and to provide you a place to download them. There's lots of other tabular data here, different spectral types, radial velocities, proper motions, gravities, companion relationships. One thing which I noticed while preparing for this talk is that we also have modeled parameters. So if someone has fit a model and derived a mass or a radius or an L-bowl, that is also in the archive. It's just currently not showing up on the website. I want to show you, so I have an example source that is not in the archive. So I know that this source is not in the archive. And so I just want to show you what happens when I search for an object that is not in there. So there are no results. And instead of getting an empty table, you get this: are we missing any expected data? Please open an issue. And then if you click on opening an issue, it takes you to the GitHub repository and the missing source issue template, where you could give us as much information about the source as you know, and to put it basically on the list of things to ingest. I still have 0355 up? Let me show you on 0355. I believe at the bottom of every source, there's also a link to open an issue if we're missing any data. Thinking. Yes, right. It's actually for if some exists, please open an issue, right? There's lots of links to open an issue if there's incorrect data or missing data. We won't know if you don't tell us. We can't fix it if you don't tell us. I also want to show you, yes. So one of the things about Simple that is great is that for that particular source, all that is the fundamental element of the database is a collection of ASCII JSON files. So you can do very sophisticated modifications like script Python modifications to the database, or if you just need to change one source, you can just modify a JSON file. So this is the information for that source that we were looking at, 2mass 0355 plus 11. Here are the modeled parameters, which I said existed but didn't show up on the website. If you wanted to add another name, right, you can see the syntax of this, how straightforward it would be to add another name, and the parallaxes, the photometry. So all the information that we have on the source is collected together in an individual JSON file. So I'm trying to show you not to be intimidated by modifying the database. At the end of the day, you would just be modifying ASCII files. All right. So that's everything I wanted to say about the website. I also wanted to show y'all a different way of interacting with the database, and that's using the SQLite browser. So there is a place, and let's see, I'll put it in the chat later, where you can download the entire database as a file. And so it's an SQLite file, which you can open with this free open source app called DB Browser for SQLite. And so I already have it downloaded, and it's right there. This is what you see when you open it, because a database is a collection of many tables. The nice thing about this is that it's a very intuitive way of navigating the tables. So if I search for 0355, I get I can filter down the sources table to see, let's see, which one is it? 2mass 0355 2337. So it filtered down the sources table. I now know, and so source is the primary key, so I can find everything about the source. Let's see, I want to know what photometry there is on 0355. Here's all the photometry and all the references now here. I guess names is also a good one. That's also here. So this is a different way of interacting with the database locally on your hard drive. You can also edit this. Like if you wanted to add your own, if you wanted to roll your own version and use it for your own purposes, you can edit this SQLite database. The other things that's nice about this is that you can run queries here. And what I really like about this is that it auto-completes. Y'all can see that little thing popping up. And so it's really helpful for helping you compose your SQLite queries. I'm not an SQLite expert, and so I always just end up Googling in order to do the kinds of things that I want to do. But let's see, we can join spectral types using sources. And so this is going to show us that I typed something wrong. Select star from sources, join spectral types using sources. I don't know. Oh, using source. There we go. And so now this is all the sources combined with the spectral types table. Let's say I just wanted to find the T dwarfs, where spectral types dot spectral type code, and we tried to be, in this case, T dwarfs start with 80, and I can hit play, and now I see that I have 1,000 T dwarfs. Return 1,040 rows, and then here's all the spectral type strings and things like that. And then you can, now you have a nice table which you could copy and paste and put it into an Excel spreadsheet and work with it. You can also save these queries and access them later. I think I am at time. Did I say everything I wanted to say? Yeah, I think I did. We can't hear you, John.
I wasn't saying anything yet. I was thinking, but
Okay.
so I saw that. I mean, just poking around reminded me that I have some spectra that I guess I never sent you. So could you remind us, besides opening the issue, what kind of format do we want to do? Right, like
For spectra?
yeah, like like if AstroPi, what did you call it? Spec something?
Specutals.
If specutals can read it, is that the best thing to do, and then you'll be fine?
Yeah.
Or is there something else you prefer?
This is such a moving target right now. I do have a way that I like doing it, but I don't want to teach everybody that way. I really want to get that into, as you know, this what I think specutals.write should do.
Uh-huh.
And so I don't want to put a whole bunch of extra burden on people to convert their spectra, especially old spectra.
Mm-hmm.
So I think that's something we should just talk about and on a case-by-case basis before you did a whole bunch of work. I am pretty sure the IRAF fits spectra, like the spectra outputted by whatever it was by the IRAF is readable. Like there's a good reader for that. Where we struggle are with some of the specs data, some of the IDL specs data. We also struggle with like tabular, if it's just, you know, rows, columns of ASCII data, that it's very difficult to read.
Thank you. Do we have questions? I mean, this is really wonderful and it's a huge effort. Do you have the resources to keep this running indefinitely? Is it a small enough database that you can do it?
Yeah, that's a
Because
great,
obviously that's been a challenge in the past, you
yeah,
know.
that's a really great question. So I am, so there's, I guess there are two things. One is that simple and databases are my primary thing now. Like this is what I really want to do with my research time. Simple has basically is the first test bed of this entire, of what I call the AstroDB toolkit, which is a set of resources which combine together. Any astronomer could roll this for their own data set. I intend to apply for grants and do all those kinds of things to support both simple and the toolkit. I did apply for a JWST archival proposal, JWST whatever we are, cycle 3 proposal to support simple, and I'm really hopeful that goes through. So of course I can't commit to having the resources, you know, forever and ever, but it is my primary research activity.
Many years ago at the first BDXOCon, one of the theorists, appealed that, it's really important for us when we're on panels and things to support that kind of science that's so, critical to all of us, but we don't necessarily, right? And I think maybe we could have that in mind for the archives too. I mean, not political campaigning, of course, but,
Yeah.
Anyway,
If
Derek has
anybody's
his
on the
hand
review
raised.
panel,
Yeah.
if anybody's on the review panel, happy to answer more questions.
Derek?
Yeah, thanks for the presentation. I'm just jumping in on the issue of reading IR stuff. So I guess there are a couple of different varieties of IR spectra out there, and basically all the basic formats should be readable already by the default readers from SpecUtils. Also, the SpecUtil system itself is designed to be modular, so you can, in principle, just write your own reader to plug it in into your own system, or ideally submit it to the folks who are maintaining it, so it can be integrated. But some of the shell spectra basically are maybe partly readable, but not really fully usable, because the AstroPy world coordinated system simply doesn't have a concept of those types of spectral coordinates. So you will be able to read the flux spectrum generally, but not really have the full and complete wavelength information.
Yeah, also to be clear, the spectra, no matter what their format are downloadable from Simple. It's just the formatting, it needs to be, in order for it to display here, it needs to be readable by SpecUtils. So it really is kind of just an aesthetic. It would be nice thing.
But of course, users downstream, they too need to be able to read it, right? And maybe the situation's just not that good for the community. And so it's great, you and Derek and everyone else who works on this. Cite the AstroPy papers, etc. All right, I think we're due for Mike now.
Hello. All right, let me share my screen. You can hear me okay?
Yes.
Okay, I'm going to tell you about the Ultracool sheet. I imagine some of you at least are familiar with it. I'll tell you what's in it, and I'll also tell you what's new with it. This, of course, is a huge team effort. A lot of this effort grew originally out of compilations that Trent Dupuy and Will Best put together for their PhD theses over the years. And I think we've all done a lot of work for this. Probably the two of them have done the most heavy lifting of this whole effort, which has been going on for a couple of years now. Okay, so I think only a very small number of us in the Zoom were actually around, or at least our brains were turned on to astronomy at the time that the first methane dwarf was discovered. But of course, we know since that time, there have been a huge number of discoveries. This is a plot of the year of the discovery paper from the Ultracool sheet. It's not 100% complete, but it's probably pretty close. So in excess now of 3,000 LT and Y dwarfs. It's hard to keep track of everything. Likewise, maybe a few more of us were, astrocognizant at the time of the discovery of the first directly imaged planet, 2MASS 1207b. And those numbers correspondingly have grown as well. The two shades of blue here represent things I think that everybody, the dark blue is things that everybody in the community would say for sure it's an exoplanet. The light blue, maybe people would like to debate it, but all this is to say there are several dozen objects now. So, you really want to keep track of all this stuff. So this is what we've done in this online resource called the Ultracool sheet. It's all publicly available. The data files are at Zenodo, and the sheet itself is just basically, it's just a Google spreadsheet. That's all it is. This is actually the tag page from the current version that's publicly available. We're literally at the very end phase of a 1.5 year effort to upgrade this. The most obvious thing from the front page is the number of objects, but there's quite a bit more stuff in here. So we're over 4,000 objects now, and we're releasing at the end of this week. So if you've downloaded this before, in a few days, there'll be a chance to upload everything, to get a new version of everything. Okay, so like I said, it's just a Google sheet. just Google Sheet that we spent 3 years on. So if you can work with a spreadsheet, you can work with the Ultracool Sheet. It has objects. Typically, we restrict ourselves to spectroscopically confirmed objects, M6 spectral type or later, distances within 100 parsec, but there is some coverage as well in the brown dwarfs and the ultracool objects in the nearby star forming regions. For the main sheet, there's over 4,000 objects. There's over 300 columns. So there's over, whatever that is, more than 12 million pieces of individual data, and also some supplementary information about the binaries and the triples I'll get into. Oh, I should say, yeah, actually, Kelly's opening comments about the stuff that the simple folks value was interesting, because I don't know if we've ever explicitly talked about the things that we value in doing this, and maybe it's just kind of built in. I think one thing we really value, probably in a borderline OCD sort of way, is that anything that we release in here is complete. You know, we're pretty good for completeness for objects, but we know we have some papers in the literature we haven't ingested. But every single thing that we put in here has an entry in every single cell, and we believe it's the best available information in that cell. And I think that's fundamentally why this takes so long, is that we really try to be, for the stuff we put out there, we really try to be complete. And also it's driven in spurts by when people want to write papers and they know there's something missing, then an effort is put in to make the new information complete as well. And that's what spurs new releases of the Ultracool Sheet. Okay, so here's a representation of most everything. It's a color magnitude diagram for things that have J minus K data, and distances either parallactic or photometric. Okay, so what's in the sheet? We have photometry from all the major catalogs and also ingested from the literature. The optical, pan-stars and Gaia, the infrared, 2MASS, MKO, UKIDS, and also UHS, and then Spitzer and WISE. Spectroscopy, again from the literature, optical and near-infrared spectral types, gravity classifications when they're available. From those, we compute photometric distances for everything. And then also astrometry, proper motions, parallaxes. We track the epochs of the different surveys, which turns out to be quite important, as I'll mention, and also moving group membership. I'll get into that some more. And then we have various subcategories: young objects, subdwarfs, companions, resolved binary components. Here's a nice representation of the wide companions that are tracked in the sheet. So this just shows it's an infographic that shows the projected separations of all the wide companions. That is ultracool companions around higher mass stars, and the colors denote the spectral type. There are 260 objects in the sheet. Binaries and triples and resolved photometry and spectroscopy when exists for all the binary and triple components. Also things like their projected separation. Some orbit information when it exists. We made a huge effort to make all the names Simbadable. That is, there's a name field that you can put into Simbad and it will return the entry if it exists. If you've ever worked with names in this field, you know it can be a real headache. If you've ever worked in the Pleiades, you know that the names in the nightmare are Pleiades. So we spent a lot of effort straightening out the names. And then we also retrieved all the baseline information from Simbad, all the many possible other Simbad names, and the photometry and radial velocity information that Simbad retrieves for every object. There's a whole bunch of notes on things that might have caught people's attention in the literature. Is it accreting? Does it have lithium? And we also flag things for exoplanet status or maybe exoplanet status. And then finally, the last year and a half, through continuing but on and off efforts for a very big upgrade, which is coming out this week. We're now over 4,000 objects. All the Gaia stuff has been updated to DR3. All the All-Wise stuff has been updated to CatWise and the CatWise astrometry. We've added L&M photometry, which we were a little short of in version 1. As Kelly indicated, we now have links to everything in Simple. If it's in Simple, there's a URL which will take you to that Simple page. And then we have age estimates, which were a lot of work, but well worth it. So we have, for every single object, we have an age estimate. I wouldn't call this a homogeneous analysis because, of course, data is not homogeneous for all objects, but at least it's consistent. It was done in a uniform workflow, and we can explain what we did. It's based on Banyan sigma and the combination of spectroscopic gravity and also information in the literature. And when those things don't agree, sometimes a judgment call has to be made, or sometimes something has been is rendered obsolete. The Banyan sigma analysis is based on all the astrometry in the sheet itself, so everything is back traceable. And there's a whole bunch of notes about it. So here's an age distribution, and everything also has error bars on it as well. So every single thing has an age. We understand that age estimates are imperfect, but at least we've made a first pass at doing this. Okay, so like I said, it's just a spreadsheet. If you can, filter or cut and paste or search in a spreadsheet, you can use this. There's a public version, and because of the way Google Sheets is set up, you can interact with the Google Sheet basically in your own little universe. You can make your own filters. You don't break it for anybody else. So let's say you want to, find all the T-dwarfs that are above Dec minus 35. Actually, this should say J magnitude less than 18, not just 16 to 18. And within 20 parsecs, say you want to build some kind of sample, 177 objects, extract their coordinates and their photometry. All the L-dwarf companions around stars that have separations greater than 10 arc seconds and have a Gaia parallax, 70 objects, so forth and so on. Very quick and easy to get into these kinds of filters. All the data files are posted, so if you want to do something more sophisticated, you can download all the CSV files and ingest it into TopCat or however else you want to manipulate it. Coordinates. Okay, so there is a field in the Ultracool sheet which will tell you the coordinate of the source tonight. Okay, so this takes all the epoch coordinates from different catalogs, decide which one's best, applies the proper motions, and corrects it. Okay, so for things that are discovered recently, it's not a big deal, but discoveries now stretch back, 20, 30 years almost, and at least for the 8M dwarfs, I think the earliest reference in the sheet is a Ross paper from 1926, so it's approaching a century. Okay, so in case you're curious, if you calculate the total proper motion of every object in the sheet since the time the discovery paper was written, here's the histogram, 800 some objects, about 20% of the sheet have moved more than 5 arc seconds since their discovery paper. So we just find this very convenient to have coordinates, ready to use when we're at the telescope. I mentioned there are 12 million different, in excess of 12 million data points collected in the sheet. Every single thing is tagged with a reference. There's a references tab, which includes the ADS code. I think there's over, I forget, we're approaching 1,400 references now. And I think I was going to upload a BibTeX library as well, maybe for the public release, so you don't have to do this on your own. But basically, every single thing is tagged. Oh, I just showed this for fun. If you wonder why it takes so long to do this, aside from the the low-level OCD, there's just a lot of changes, and we internally track every single change that is made. Here's a plot of these so-called history tabs. We keep a track of every delta. I think over 1,000 entries of these, and this large spike is basically, I think I ran this last week, so it's the stuff leading up to the public release. So we keep very extensive notes of everything. And there's also version control as well. Okay, I wanted to show just a little bit of science that you can do from sort of this very large collection, 2 student-led projects. So we have photometry, spectroscopy, distances, parallactic and photometric, and also age estimates. And this is merged with the Specs Prism library, at least the previous version, and some of our own spectra as well. Andy Katsangi did an RU project with me. He's not a grad student at Caltech, where we took all the photometry and all the spectroscopy and integrated it all to get a uniform analysis of bolometric luminosities. So I think there's more than 1,200 objects in his paper. And from those, we use the age estimates and the bolometric luminosities to derive fundamental properties from evolutionary models like temperature, gravity, radii, and masses. So it's a very large analysis. And so you can do fun stuff like this. Like, for instance, this is a color-coded CMD, which shows the temperature derived from evolutionary models. As you move across the CMD, things go from hot to cold, kind of fun stuff. We also do a direct head-to-head comparison between temperatures and gravities and radii measured from evolutionary models and those you get from fitting the spectra, the near-infrared spectra, with the BT settle models. And so it's a very large-scale look at some of, I think, discrepancies that are known between this head-to-head comparison, but have never been looked at the scale of, say, 1,000 objects. I think it's well known that, for instance, the radii you derive from fitting spectra, the R squared over D squared normalizing coefficient, does not agree with atmospheric models. This was noted perhaps most prominently for the 8799 planets. But here's a map of how that behaves over the whole color magnitude diagram. So the famous directly imaged planets down here, the discrepancy typically is the atmospheric model radii are smaller than you expect from evolutionary models. Turns out there's a similar discrepancy in the opposite sense at the ML transition, at least when you use the BT settle model atmospheres. And there's a breakdown in the paper versus various other secondary parameters about how this behaves. And I should say all of Etiquette's bolometric, all these calculations are also in the Ultracool sheet as a separate tab from his paper. We took this a little bit farther with Spencer Hurt, who also did a REU project with me. We did it specifically for the young moving groups, members of the young moving groups, and we looked in more detail at sort of the spectroscopic residuals as a function of wavelength. The idea here is that, you can fit a single object and you can see some discrepancies, and you can see some other discrepancies as a function of spectral type, but normally you only have the opportunity to fit a few things. So we fit them all. He builds this whole thing into this Bayesian framework in this paper. So it's a homogeneous analysis. Paper's now out of almost 90 objects in young moving groups using BT settle. There's a breakdown of the ways in which the models work and don't work, again, through this framework of evolutionary model versus model atmosphere comparison. One of the very interesting results is this is a plot of the normalized residuals, basically data minus models, minus observations as a function of spectral type. And so Spencer basically finds that the residuals are strongest at the M to L transition, which I think was a little bit of a surprise to us, because I think classically the wisdom is that, models don't fit well directly imaged planets, which are late L, 87, 99, and so forth. But in fact, when you look at this in mass, it's really the ML transition where dust is onsetting that is a real problem. And then Spencer discovered that if you build in, if you add just an extra ad hoc parameter to the BT settle models where you put in some ISM dust and allow that to free fit, you can actually improve the fits quite a bit. And this shows the best fitting AV, the equivalent interstellar extinction you get as a function of spectral type. So you need an increasing component through the ML transition, and then you need very little or even negative ones for the mid-L. So the particular recipe used to model onset of condensate formation and as the clouds thicken doesn't actually match the observed spectrum, but including an extra component does help out quite a bit. Okay, to find us, we're really easy. All you have to do in Google is type Ultracool sheet. If you type Ultracool sheet, it takes you to the Zenodo page. There's a link to get to the Google spreadsheet. You can type Ultracool sheet as well with a space. That works too. However, if you type Ultracool sheets, you will not get to us. You'll get to the Amazon page, and that will sell you some very nice sheets, which currently are on sale. Okay, so that's it. Like I said, this week there'll be a public release. And of course, we welcome contributions. If people have some other contribution of, say, V-sine eyes or something like that, metallicities of host stars, we don't have those. We would happily take that stuff. And that's it. I look forward. If you got any questions, let me know.
It's great to see the links back and forth, between the different groups and databases. That's wonderful. Sorry, spreadsheet, not database. Richard, is his hand up?
Michael?
Yep.
You can hear me? Yeah.
Yep.
When you say the best data, how do you decide? Like in parallaxes, do you just use the lowest error, or do you consider yours better than ours, as it were?
No, we use the lowest error. We use the lowest error just to make it simple. There's just too many judgments to make otherwise. I should mention we also have a
choice of spectra as well.
Well, so the spectra is a judgment call, right? If different people publish different spectral types, we write down the one we think is
really, you've gone through one by one.
What's that?
Really, you've gone through one by one. Good Lord.
Yeah, that's right. That's right. That's why it takes a year and a half to do an update. I should mention also, we have a column. I think we weren't going to include it in the public release, but maybe we should. You have your own catalog, and I know that you and Trent did a cross match, and so we have a tag. We have a cell which gives your corresponding name to our corresponding name as well. That allows the two things to be cross-referenced.
Public sheet yet, Mike. So
yeah, maybe we should release that in the public sheet. I don't see any reason why not to do that.
So just to talk about how Simple handles that. So that's one of the nice things about a database is that we can have multiple measurements for things like spectral type. But when you do a query, a lot of times you just want one spectral type or one proper motion or one parallax, even though there's lots of measurements. And so we use something called an adopted column in tables like that. where one can indicate which one of those you want to adopt. And then we haven't yet, but we also want to write scripts where you could imagine one for whatever kinds of reasons would want to change that adopted column for different types of analysis. So yeah, we used to call it the best column, and that's not correct. It's not always the best one. It's whichever one makes sense for whatever science you're trying to do.
Yeah, Kelly's right. We don't track multiple measurements. We just take the one.
We do track, just to chime in, we do track, if something is observed in Gaia and it has some literature measurement, we do have those distinct from each other.
That's right.
And Will's Eucurt sample, but it's a very niche thing. But in general, we do have, actually, you could compare Gaia and literature parallaxes if you wanted to.
If no one else is asking a question, can I ask another one?
Sure.
In one of the first Ultracool Dwarfs, you actually put out a table where you had all the parallaxes, for example, that you had considered. That's not going to be put out, I suppose, this time. It's too much work.
That was my database of ultracool parallaxes from 12 years ago, and yeah, no, that had a separate tab that tracked all the parallaxes we had considered, and we don't keep track of that anymore.
Yeah, Elliot?
So I'm kind of presuming that if there's, say, a companion and it's not been resolved, then it's going to be listed as one entry in your table, right? Like such and such AB or whatever. Am I mostly right there?
We have the multiplicity thing is very interesting. For unresolved sources, the integrated properties are listed in the main sheet. We have a thing there that a column which indicates it's an unresolved source. We have a separate tab with binary information that lists all the resolved photometry. And we do the same for the few known triple systems as well. And then there's also the interesting case where if it's a binary, but both components are ultracool dwarfs, but they are resolved, then of course, then in that case, that resolved information is listed separately. But again, through the Seller cell, you can flag cases that are in that as well.
So at what point does it graduate to getting its own separate, the one becoming two? Like if I resolve it once, is that enough, or is there like a threshold?
Yeah, so for the main sheet,
you can go ahead, Mike. Sorry.
I was gonna say maybe Trey can actually say, maybe correct me if I don't. For the main sheet, because it's a large part of it is like optical, near infrared, mid infrared photometry from 2MASS and CatWise and that kind of stuff. If it's unresolved in those catalogs, that's typically what causes it to have a single entry listing, and then all the extra resolved information goes in this other area. Is that a fair summary, Trent? I mean, under all these,
yeah, so it ends up being around an arcsecond, but yes, it's essentially if something's been known as a resolved object for many years in 2MASS, for example, but it's not resolved in WISE, right? We're not gonna demote it because WISE didn't resolve it, right? So, but in general, if it's been resolved by some survey, so probably the highest resolution would be something like UKIDS or VHS or PanSTARRS, then it counts as a separate thing. Especially if somebody got like spectra of the two objects without adaptive optics, right? That's another way of thinking of like, if you could get spectra of them from specs.
Yeah, I was saying in general, we try very hard to tag our choices. So and give the information if you want to make other choices with other filters. So if in this multiplicity thing is also one of these things that can be very like I said, a lot of edge cases if you think hard about it.
Thanks.
So in simple, the way we handle it, right, this is also really challenging. In simple, the way we handle it is we would have that, if it were an unresolved binary, we'd have three different sources. We'd have the AB as a single source, then we'd have the A source, and we'd have the B source. And And so, and the data would be organized accordingly, however it makes the most sense. And then we have a companion relationships table that basically says the relationships between all the components.
I love that. That's such a good idea.
And I'll just throw in a comment real quick that the other thing that the binaries tab essentially kind of does is, if you remember a website called vlm-binaries.org, it used to be like the dwarf archives of Ultracool Dwarf binaries. Anyway, and that was a side project for a while that I was going to try and reinvigorate that. But essentially, the binaries tab in the Ultracool sheet essentially does that. And I think we have 170 something binaries now. So.
Maybe we should move on now, or are there any other?
I have to run to go host a visitor. I regret I can't stick around for the rest of the meeting, but see you.
Thanks so much for the talk.
Brent and I can keep answering questions about Ultracool Sheet if anybody has them via Slack or whatever else. This is Will Best.
Okay,
I also
Nicola.
got to drop off. Nice seeing everybody.
Thank you, Kelly.
Hi, can you hear me?
I can.
Okay, all right. I'll share my screen then. So I hope you can see it. Do you see the full screen?
Yes.
All right. Okay. So good afternoon, everyone, or good evening. So thanks to John for allowing me to give a talk a week later, because unfortunately I could not be there last week for some personal reasons. So today my goal is to present the science that our group at the ISC in Tenerife aims to carry out over the next years or decade related to LSST Rubin. So as a summary, I would like to say that our group will focus mainly on two major topics that will exploit the depth and astrometry and coverage of both the Euclid mission and the Rubin LSST Observatory. So on the one hand, what we want to do is to identify the first halo brown dwarfs and also characterize this population of objects that preserved the most pristine material from the Big Bang. And on the other hand, we want to investigate the low mass end of the mass function, mainly below the deuterium burning limit in the solar neighborhood, but also in young moving groups, open clusters, star-forming regions, with a special focus to really the coolest objects and the coolest members. If we can reach 1 Jupiter mass, this is our long-term goal, let's say. So before I want to go in more details about each of the project, doing some publicity on the work that we've done as well within the group. Here I'm showing a plot from a paper we published in 2022, and now that I heard about the simple database and the Ultracool sheets, then I guess I might have to update this plot with more objects that are the L and T dwarfs with parallaxes. So we're plotting the luminosity on the y-axis, and then on each diagram shows different colors that are available for some of these brown dwarfs with parallaxes. And on top of that, we've overplotted WISE 1810, which we think is possibly the first brown dwarf, metal-poor brown dwarfs within 10 parsec. And we also added WISE 1534, also known as the accident. And if you focus on the right-hand side plot, where we're plotting the luminosity as a function of the WISE W1 minus WISE W2 color, then you can see that these objects in addition to possibly two others here in this diagram, may actually show a sequence of metal poor objects that clearly lies to the left-hand side of the main sequence of the LNT dwarfs with parallaxes. So we start now to be able to investigate the metal poor objects at those spectrum types. What is the current census of metal poor dwarfs? I would say that right now, I don't know any metal poor brand dwarfs with a metallicity below minus 1.5 dex. However, we do know some objects that are metal poor. We know the T8 companion to Wolf 1130 with a non-metallicity of minus 0.64 that was discovered like already a decade ago by Mace and collaborators. And then we have WISE 1810 that has a metallicity of minus 1 dex, or maybe a bit lower, and that we put at 9 parsec, thanks to some trigonometric parallaxes that I will present later. And then we have the accident, which is possibly the first white-type isolated metal poor brand dwarf that remains a candidate. This was published by David Patrick and collaborators. And Aaron is present today as a James Webb proposal that many of you, I guess, know, to characterize further this object. And we plan to complement that with some optical imaging that we got granted with both GTC and the VRT to complement the James Webb data. Now, if we move into the LSST era, I think that we should be able to see all the M subdwarfs that are brighter than 24.5 in R band. So there's a single shot with LSST up to about a kiloparsec. If we want to look at the subdwarfs, L-type subdwarfs, we might be able to see them up to 30 parsec. If we want to go for the T dwarfs or T subdwarfs, like WISE 1810, we might be able to see them up to about 50 parsecs, but only in the two reddest bands on a single exposure. If we want to go to later spectrum types, we would need to wait for the final images. But all of these are like estimates, because we're really doing those estimates based on only a few objects. So we need definitely more data to have a better estimate to know all this population in the Milky Way. Now, the search for proper motion is obviously very important. This has been already discussed, and we want to find the brown dwarfs that are moving in the LSST data. As an example, again, I take WISE 1810, where you can see on the top right the images that was one of them was taken with the UKIDS Galactic Plane Survey in 2010. You can see the object that is marked with a red arrow here, and he has moved. 10 years later, he has moved quite significantly. This is an optical image obtained with the Nordic Optical Telescope in La Palma. Really, 10 years later, you can see how the object has moved from here to here. The difference in flux comes because we're having an infrared and an optical image. We also are able to determine the space motion for this object lies here around, I would say, typical of a disk star. Doesn't have a huge space motion, although it has a very large proper motion. Then the parallaxes, obviously LSST will go further than Gaia and will complement Gaia at much fainter magnitudes. WISE 1810 is the good example. So with the repeated observations that LSST will provide, we should be able to get parallaxes for this type of objects. Obviously, WISE 1810 will be a good template in that case when we get several epochs from LSST to see how accurate we can determine parallaxes for such faint objects that we can detect in the optical. In that case, we place it at 8.9 parsec with an uncertainty of 0.7 parsec. This was done with time on the GTC telescopes, so in the optical mainly, although we have some data from the infrared, but most of the data comes from the optical. And then obviously we want to do some all sky searches for brown dwarfs with a special focus on the subdwarfs. For that, we can cross-match LSST and Gaia for the high mass end or the brightest end, but then we want to move towards cooler objects, so we will have to look at visible and infrared survey, but then more focused on the infrared survey ones because we want to go deeper and find cooler objects. And then many of you, I suppose, have heard talk by Eduardo Martin, who is head of independent legacy survey team that has access to the Euclid mission. And we plan to cross-match the data from Euclid and also LSST to be able to find some interesting objects. All of this, our goal is to find new objects that we will incorporate in this archive that we have in the Spanish Virtual Observatory, where we compile the ultracool subdwarfs we found over the past years. We have some M subdwarfs, we have L subdwarfs, and we plan to keep tracking these new discoveries for metal poor objects. I'm also doing some searches at the moment, mainly focusing on the L subdwarfs using visible and infrared public surveys. We've been using Sloan and Pan-STARRS, cross-matching with UKIS and VHS, where we have several thousand of square degrees in the entire sky, because these are really wide surveys, large-scale surveys. We have also preliminary spectroscopic follow-up for the brightest objects, some of the faintest ones as well, with the GTC to confirm their nature, their metal-poor nature. This is a paper I'm trying to finish. Hopefully, I will be able to send that to the journal soon. But there's still a lot of work to do, especially in the spectroscopic follow-up, because we have more than 1,000 candidates. And this is mainly a photometric search at the beginning. So that's the first part on the metal poor objects. Now, the second part I wanted to mention is the work on the clusters. As a first example, I wanted to highlight this work we've done with Ricky Smart on the IIDs and basically looking at the members of the IIDs with Gaia, to which we added parallaxes from the ground for 10 brown dwarfs members of the IIDs. And so we were able to have a 5D view of the IIDs with the space motion. And I think the best way to present it is this movie, where we have a 3D view here, and we plot the non-stellar members of the IIDs in black. The size of the dot represents the mass, so the bigger the dot, the more massive is the object. You can see most of the objects being really in the central region of the IIDs, but some of them have been already ejected. Oh, sorry. And we added to that the brown dwarfs, for which we got the parallaxes from the ground, as well as the white dwarfs. This is a paper that we published back in 2019, and more recently we have extended this work to all nearby clusters within 500 parsecs and ages less than 1 giga-year. This is a work that Marusha Seshal did. I think she's connected today, and she was funded by the Canadian government to compile a list of members and distances per motions to revise that for all these clusters. Sorry. And then we looked at the luminosity function and how this luminosity function, the shape of the luminosity function evolves with age. So this is a paper published last year. And we have also a website where we compile all this information of the members. And you can also look at different diagrams. And also Aladdin viewer of the object. So that this is a significant database for members of clusters. But then with LSST, obviously, we will be able to go much deeper. If you focus on the plot I'm showing on the right-hand side, I'm plotting here the Z versus minus Y, Z minus Y, sorry, color as a function of the Z band. This is from Pan-STARRS photometry. You can see that at the very bright end, brighter than 14, well, even Pan-STARRS is saturating. That's why you have many objects here. But then you can definitely see the sequence of IIDs member that goes all the way to the brown dwarf regime, as we've shown in 2019. But hopefully with LSST, we think we can reach the deuterium burning limit, and maybe we might be able to see even some planetary mass objects if they do exist in the cluster and they have not been yet completely ejected. So this is basically the case of the IIDs, but obviously we want to transpose that to other clusters as Marusha has done for the clusters with Gaia. And so that's about it. I wanted to show today. I just want to highlight that there are several members of the group that are collaborating on those projects. I guess you know most of them. And with Eduardo, mainly, we will be the people looking at the LSST data. And we have also a PhD student who is also connected today, Yulian Zhang, who is doing his PhD on the meta-poor brown dwarfs. So he will definitely participate in this project. So thank you very much. Thanks for coming and listening.
Thank you. I guess while anyone considers whether they want to ask a question, I'll go ahead with one. I guess with LSST, always the challenge is going to be spectroscopic follow-up, and maybe here, you know, what do you think is possible in terms of getting, say, radial velocities, right? Which would obviously be, you know, really wonderful to get the 3D motion for the halo objects. Do you think?
So
do you need a 30-meter telescope, or is that even enough? I mean,
yes, that's a good question. Well, for the brightest things, I guess we can use we can start with a 10-meter telescope. We have obviously access to the GTC, and that's part of our contribution, I would say, to try to do some proposals to request time and see what we can get. There's some instruments that may help. We have to see how deep we can go. Obviously, that's the main issue. There is the Megara instrument that can do a higher resolution to do the radial velocity. And then there will be a new instrument that will be combined to the optical spectrograph that should be more sensitive. So hopefully we can go a bit fainter than we can do right now. But yeah, we might have to wait for the ELT to go all the way to the depths of LSST. But maybe that's not too far away, right? I mean, they're claiming 2030, maybe for the...
Speaking as someone in the States, I'm very jealous of your progress. But pleased with it, of course.
Yes, yeah. Well, I guess one of the idea, I mean, for the ISC contribution is really to contribute with some access to the 10-meter telescope time that we have. So if anyone is interested, I guess we are here to collaborate and do the best science we can with LSST. So
yes. I'm checking the Slack. Are there any other questions? Okay, well, we are behind the original schedule anyway.
Yeah.
I think that Joshua should be next. And Joshua is joining us from Australia, if I'm not mistaken. So thank you, so much for what is obviously an extremely inconvenient scheduling choice in terms of you. So
that's all right. Thanks very much for having me. Okay, can everyone see my screen?
Oh, yes.
Yep, great. All right. So hi, my name is Joshua Pritchard. I have just completed my PhD at the University of Sydney. So yeah, I'm dialing in. It's 6:20 at the moment over here. So it's not too bad as far as time goes. But I've been mostly catching the meeting on the recordings over the last week. So it's been really good to see all of the awesome things we can expect from LSST. I'm going to talk to you today about some of the work that we've been doing in the radio band to understand ultracool dwarfs and in particular how radio emission can help us to understand their magnetism. and hopefully touch on a few overlaps between LSST and radio astronomy over the next couple of years. So just going to briefly touch on the emission from ultracool dwarfs that we observe in the radio band. We tend to see two different kinds of radio emission: quiescent emission, long-lived, slowly varying, existing sort of over months to years timescales. Emission occurs in ultracool dwarfs and brown dwarfs that is generally associated with non-thermal electrons, with plasma that is being accelerated inside of radiation belts. So similar to the Van Allen belts that we have around the Earth and that we see from Jupiter. This drives a radio emission mechanism called gyrosynchrotron emission, and it varies fairly slowly, typically not going to see a strong variation in flux over the course of a single observation, but you can track it sort of over many months. The other kind, which is mainly where my interest lies, is auroral emission. And so this is a radio emission that's associated with auroral processes that you would be more familiar with in the optical and infrared bands. And so this is where you have energetic electron beams that are being channeled along magnetic field lines. As those electrons impact the atmosphere of the star or the planet or the ultracool dwarf, you end up getting optical and infrared and X-ray emissions generated by the ionization and impact of the electrons with the atmosphere. But you also get radio emission generated by a resonance between electrons orbiting around the magnetic field lines and circularly polarized radio waves that are rotating with the same frequency as the electrons. And so this is a process called the electron cyclotron maser. The important thing to know about it is that it produces a highly directed beamed emission, and it's not like a linear beam, but it's into a hollow cone. So that's what I'm showing here with the sort of green disc-like structure here. So it's projected 90 degrees away from the orientation of the magnetic field, and you only observe the radio emission when you see this edge on. So as you watch the ultracool dwarf or the brown dwarf or the planet rotate, you only get a burst or a pulse of emission as it lines up like right now. And so this gives rise to very bright, intense bursts of radio emission that are only observed over the course of anywhere from minutes to hours. This is also very useful because the frequency of the electron cyclotron maser emission is directly tied to the local magnetic field strength. And so this is actually the best probe that you can have of a remote magnetic field. So we see this kind of process, this auroral radio emission, in many different kinds of stellar system and also within the solar system, of course. One of the best prototypes to understand how we might understand this emission in ultracool dwarfs is Jupiter and the Jupiter Io system. So there are two broad ways that this emission can be generated. What you need is a source of non-thermal electrons, so plasma that's been accelerated by some kind of energetic process, and also a strong magnetic field to channel the plasma down into the atmosphere. And so the two main engines that drive this emission are a breakdown in co-rotation of plasma with the magnetosphere of the star or the planet. In the case of Jupiter, that plasma is being generated by Io, the volcanic moon, and that plasma co-rotates with the Jupiter magnetosphere, but can't keep up. It can't rotate like a rigid body. And so as it lags behind and has differential motion against the magnetic field, this drives an auroral current system, which is shown here by the orange and the blue lines, which drives electrons down into the atmosphere and generates both ultraviolet and infrared aurorae that you can see on the bottom left, but also that coherent radio emission that we're interested in. So this is one process that can drive it, just a rapid rotation of an object causing a breakdown in that plasma co-rotation. The other kind that we see in the Jupiter system is like electrodynamic interaction with the satellite itself. And so being a magnetized object, as Io itself moves through the Jovian magnetosphere, it generates its own auroral current that gets deposited down onto Jupiter's atmosphere. And the interesting thing here is that that moves around not like in a full oval, the way that we might see with the first process, but it moves around on its own little hotspot. And so on the left-hand side here, you can see a hotspot that corresponds to where the magnetic field line threading through Io lands onto the atmosphere. And so this is something that we also anticipate should be happening in exoplanet systems, but has yet to be discovered. Okay, so with a bit of background on the radio mission that we're looking for out of the way, the main instrument that we've been using over in Australia is ASCAP, the Australian Square Kilometre Array Pathfinder. So this is a short overview of its capabilities and what it is. So it's 36 12-meter diameter dishes that form an interferometer. And so performing interferometry with this array, you get resolution at about 10 arc seconds, and we can measure positions to about a 1 arc second accuracy. We cover a band from 700 megahertz up to 1800 megahertz. There's 3 bands that we can observe in between those 2 ranges. We tend to focus in our group, the variables and slow transients group, on the low band, which is centered on 890 megahertz. The main thing that you get from ASCAP, though, and what makes it such an amazing instrument, is the 30 square degree field of view. So I'm showing on the right-hand side here a typical ASCAP image. And for context, here is the scale of the moon. So we're covering a very large patch of sky at once, which makes it an excellent unbiased wide field search instrument. We can tile the sky very quickly, and so we can perform unbiased searches for radio transients very quickly, which is the focus of our group. And we also collect data in all 4 Stokes parameters. So we get full polarization information for any objects that we might detect in an image. Just to show you what the radio images look like a little further in. On the top left here, this sort of weird snake-like structure is a radio galaxy, and these are jets that are being ejected from it. Our group, we tend to try and avoid things like this, as pretty as they are, because they're on cosmological distances, and we're not so interested in these things that don't really vary intrinsically. All of the objects that we're interested in will be these point sources that you see in the background and are unresolved. Okay, so I'll quickly touch on 2 surveys that we've been using with the ASCAP telescope to search for transient objects. The first one is called the Rapid ASCAP Continuum Survey, and this is an all-sky survey that goes up to +40, +50 declination. We've completed 4 epochs of this survey already, and almost completed a 5th, and that spreads across the 3 different frequency bands. But we've already had 2 passes of the low band that we've mostly been focusing on in our group, VAST. And the second survey is the survey that we are driving with the ASCAP telescope, variables and slow transients. So we're interested in transients that occur on seconds plus timescale. So anything from stellar flares and short sort of transients to these extragalactic transients like a supernova and so on. So this is the footprint of our survey. The yellow squares here are a pilot survey that we've already completed and that I'll share some work from. No, I won't, sorry, but this is a pilot survey we've already completed and fully investigated. Now we are conducting the full survey, which the other bands here are showing. And so we visit the galactic footprint on roughly a monthly cadence, and the other footprints a little bit less often. We do also overlap with I think most of the LSST deep drilling fields. Okay, so I'll share a few results in Ultracool Dwarf science that we've managed to produce so far from both the Rapid ASCAP Continuum Survey and VAST. These plots are called dynamic spectra, and what they're showing is frequency on the vertical axis, time on the horizontal axis, and the color scale is showing flux density. And in this case, both of them are showing circular polarization. So this you can imagine the telescope, even though it's looking at an entire patch of the sky of 30 square degrees, we're just sort of treating that as a single pixel and saying how bright is the sky over the course of the observing window and across the bandwidth. And so we've removed all of the other emission, and we're only looking at one source within that image. And so this is the emission from a T8 brown dwarf. This is actually the coldest, latest type brown dwarf to be detected in radio to date. And as you can see here, has this periodic structure in its emission. Every 1.9 hours, we get this sort of double pulse. And so on the left-hand side is some lower spectral and temporal resolution data from the Australia Telescope Compact Array. We did follow up with another radio telescope, the Meerkat telescope in South Africa, which is much more sensitive. And you can see that the emission breaks down into this sort of bright pulse, followed by a few secondary pulses afterwards. And the repetition of this is understood to be due to the rotation of the brown dwarf. And so, like with the animation I showed earlier, we're getting the cone of emission sweeping past our line of sight. And we're getting a strong pulse leading, and then sub-pulses as the rest of the cone sweeps past our point of view. The animation that I showed earlier is a little bit oversimplified. The geometry of this emission is much more complicated than a simple cone. It varies in frequency, and depending upon the configuration of the magnetic field and the plasma properties, it can get very complex. So what we're currently interested in doing is trying to model the emission in this dynamic spectrum to understand a little bit more about the in situ properties of the magnetosphere around this dwarf. Sorry if you can hear my cat going crazy. Another interesting target that we've been looking at over the last few years is an ultracool dwarf at the end of the M sequence. So this star is quite different to the brown dwarf. The brown dwarf that I just showed had a 1.9 hour rotation period. This ultracool dwarf is much slower in rotation speed, 14.1 hours. And the inferred age of this object is about 4 gig a year. So for objects with strong magnetic fields and radio emission and this kind of variability of magnetic activity, this is actually quite an interesting object. It's much older and slower than any other ultracool dwarf that has been detected in radio to produce these auroral pulses. So I'm showing the light curve and periodogram with this 14.1 hour rotational speed, a rotational period. We detected 100% circularly polarized pulses that are driven by that auroral emission with ASCAP, and then conducted a lengthy follow-up campaign. On the right-hand side here is the ASCAP data from a 2-week period that we collected over about 5 or 6 observations. And when you fold the radio emission to the 14.1 hour rotation period, you get this really beautiful pulse structure showing that this is just a persistent auroral site that is sweeping into view over each rotation. What you can also see here, though, on the bottom panel, I'm color coding things by how long has passed since the initial detection. And you can see that the emission site actually decayed over the course of these 2 weeks. So they're not there eternally. They do have an engine driving them. And as that dies out, we lose the emission. And so you can see that this one died out over 2 weeks. And a few days after that, we used the Australia Telescope Compact Array to follow up the object again and detected another pulse. This one does not line up with the ASCAP pulse, and it's also opposite in polarization handedness. And why that is interesting is the polarization handedness tells you about which hemisphere or which magnetic polarity the emission is originating from. And so this is giving some indication that there is quite a complex structure to the magnetic field. I'll quickly just skip through the next few slides of other results that we've had from this star. We conducted a 2-year monitoring campaign with a radio telescope to see how this emission evolved. We caught lots of this repeated pulse every rotation emission. So here I'm showing 3 consecutive rotation cycles with a pulse detected on each one, all aligned in phase. And we've also seen some one-off bursts that are occurring over much shorter timescales. The original pulses were over about 2 hours, and these ones are only over minutes timescales. And so these are perhaps probing more intrinsic variability and not the kind that is driven by rotation. So there's lots of interesting stuff happening with this star. We're still investigating this a little further and trying to use these observations to model some of the intrinsic parameters of the magnetosphere. But after talking a little bit about what we've been able to do so far, I wanted to just touch on what we might be able to do together with LSST. And we are able at the moment to detect ultracool dwarfs and brown dwarfs out to a distance of about 50 to 100 parsec, depending upon the luminosity of the object. They vary a fair bit in luminosity, but this is the range that we're capable of detecting them at the moment. The problem is that for particularly the later type brown dwarfs and ultracool dwarfs, it's very difficult to get optical or infrared counterparts to confirm this as a brown dwarf. And so we have a lot of candidates that are radio transients. We just see something in our radio image, but we don't have any other multi-wavelength counterpart to associate it with. And so usually we can only get limits over most of the sky of 16 to 22 magnitude, depending upon survey coverage. And we're finding too many of these to apply for every single one to have a systematic campaign of deep infrared follow-up. So LSST is going to be fantastic as an all-sky reference, going much deeper to 25th or 26th magnitude, and will allow both for us to find more objects that we can search for in radio, but also maybe identify some of these radio objects that are otherwise unknown. And on the science side of things, I'm really interested in the capability of LSST to detect the radio and the optical and infrared emission from these aurorae. On the radio side, we can provide a magnetic field strength from the emission frequency, and also with a little bit more work and modeling, perhaps get to the orientation and the configuration of the magnetic field. But on the optical side, the optical variability can probe how much of an auroral current is being deposited into the atmosphere and where that is occurring, and also the ionization fraction of the atmosphere. So this might be difficult given that the variability is over hours-long timescales and not the short timescales that LSST imaging will occur over. But maybe we can detect this through epoch to epoch variability. And so I also hope that the magnetic field measurements we can provide on the radio end might be useful to some of the evolutionary models and modeling that other folks in this community are using. All right, so I'll leave it there. Thank you.
Well, very good. I asked a question in the chat that's already been answered, which was about, how good your positions are for, associating the sources. So I guess the answer is very good, right? 1 or 2 arc seconds, something like that. I understood it right.
Yeah, so about 1 to 2 arc seconds. And then, yeah, as Tara mentioned, we have follow-up instruments that typically, if we need better than that, we go to those instruments that can get down to, a fair bit better than that.
Okay, so Trent has his hand raised.
Yeah, so actually, just following on that, how much better do you get with follow-up for something like 1845?
The main instrument that we go to do follow-up with is the Australia Telescope Compact Array, and depending upon where in the sky the object is, we can get astrometry that is down to more of the 100 milliarc second kind of range. It varies a lot depending upon where in the sky the location is, just due to the way that radio telescopes actually form an image in the first place. Yeah.
Okay, that's interesting. And so my actual question, it's related to my actual question, which is, 14 hours is a pretty fast rotator, and there is a T-dwarf in that system. Yeah. In the SCR 1845 system, so and separated by, I don't know, several tenths of an arc second at least. So potentially the astrometry could distinguish. So is it possible that the radio emission could be coming from the T-dwarf?
In this case, I think the system is 4 parsec away, and it is a 4 AU orbit. orbital separation. So the angular separation, I think, is on the scale of an arcsecond, maybe 2. So we've looked into whether it could be the T-dwarf, and we're fairly confident it's not, and that it's the Ultracool Dwarf. We've also followed this up with the compact array and have much better astrometry than the 1 arcsecond ASCAP position. So yeah, we're sure now that it's the Ultracool Dwarf and not the T-dwarf. But at first we were considering whether it could be the T-dwarf. Yeah.
Okay.
And we have another question. Go ahead.
Yes, hello, thank you for your talk. I was wondering if you, in your survey, have any idea if more of the radio signals that you're seeing are coming either from a flare or an aurora? Like, do you see many flares that are emitting the radio, or do you see mostly other types of emission, like the aurora that you're studying?
So more generally beyond ultracool dwarfs, we detect a lot of I guess what you could call flare type emission. So the radio emission, there's not necessarily a one-to-one correspondence between optical flaring of stars and the radio emission. There's a lot of things that happen between whatever drives the optical flare and what might drive subsequent radio emission. But a lot of the things that we detect in radio are earlier type M dwarfs, like early to mid M dwarfs, that we expect are mostly due to some kind of stochastic, like solar type flare behavior, or otherwise they're also known to produce this kind of auroral emission. So there's an overlap between the two categories. Both of them can produce the very high levels of circular polarization that we detect. When we move more towards the ultracool dwarf end and the 2 objects that I showed here, they are not expected to produce strong flares. The ultracool dwarf, the late type M dwarf, there's some emission that we've observed over the course of our monitoring campaign that could be due to some kind of more stochastic process. But the signature that we mainly can very strongly associate with aurorae is this kind of broadband, very linear feature in the dynamic spectra. So that is like a hallmark signature of auroral radio emission and electron cyclotron maser. So usually we're not sure until we're able to form this data product and see a little bit more closely what the emission looks like.
Okay, thank you.
Yes, and as Tara mentioned in the Zoom chat, we're very new to LSST and very open to collaboration with people from this community. So please talk to us if you're interested in collaborating.
Do you see much effort to sort of get simultaneous? I mean, presumably LSST maybe publishes its schedule, what it's going to do tonight, and so you could conceivably pick one or more fields and try to match them at the same time. Or the deep drilling fields maybe will sort of have better light curves anyway. Maybe you would visit them sometimes on the same night. Do you see that as as being valuable?
Yeah, I think that would be
plans?
I think that would be fantastic. In general, ASCAP is a survey instrument, and we have not a huge amount of control over the scheduling, but for these kinds of large synergies between instruments, there is the potential to submit dedicated campaigns with more constrained scheduling. So that's definitely something that I think would be plausible. And also the other instruments that we use could be interesting if we have a particular target that we are interested in focusing on. So if we've already visited a deep drilling field and we've got a set of candidates of ultracool dwarfs within the field, then we could use another smaller field of view instrument as well simultaneously to just focus on those. And yeah, I'd love to talk more about the kind of timescales that LSST might be able to monitor in time domain, because there's lots that would be very interesting to get simultaneous observation. In particular, this infrared and optical aurorae, I think it would be fantastic to see simultaneous observations of that. There's only one result a few years ago, back in 2014, by Greg Hallinan, that has caught optical side of this at the same time as radio.
And of course, you know, I guess the same as using the non-survey image on the optical, it could be that the right choice is to, you know, since if you have the target, then maybe a, you know, a pointed thing that gives a denser sampling in time might be the right way to go. Instead of LSST as a survey instrument, you know, something else. Wow.
Yeah. Yeah, I'll admit I'm not too familiar with the capabilities for how much time will be allocated for those kinds of things, but that's absolutely something that we'd be interested in doing as well.
Any other questions? Well, that's our last scheduled talk. I would like to thank all the speakers, you know, for all 3 days again, for what for me at least was extremely interesting series of talks. So I guess you know, if there, you know, is a weakness in the organization of the meeting, it's, you know, certainly been on the side of how to organize discussions and so forth. So hopefully this has really, you know, sort of attracted your interest. And so I would really like to encourage people to just try joining formally the Stars Milky Way Local Volume collaboration. I promise that the current co-chairs will, you know, respond on a reasonable timescale. In the past, sometimes when I was in charge, things could get lost for 6 months or something like that. For Nicholas in particular, I know that happened. So we promise, you know, faster responses. And then, you know, we could sort of move forward with a working group and, you know, try to think of what would be the right way to move forward in terms of, you know, following up sort of all these different exciting science ideas and sort of preparatory things. So that is sort of an outcome that I would certainly hope might happen. And then we could really get the Solar Neighborhood Working Group revived. And also joining will get you into the LSSTC Slack, which, as we've heard a couple times, is a really great way to get responses from people who are, you know, deep in the project when you have technical questions. You know, like, for example, how will the crowded field pipeline work? And how has it changed from what they said 2 years ago or whatever? Okay. Would anyone like to speak at this point or make a suggestion for if there's anything that's worth doing by Zoom right now in terms of discussions, as opposed to sort of a future email, Slack, etc. Endeavor? I know that I, for one, would like to aim for getting sort of a catalog of everything within 100 parsecs, not the Gaia one, because of course, Richard L. Smart has already provided us that, but for the cooler things, right? And then you would, you know, be able to put that into alert systems and plan observations. I think would be really, that would necessarily, you know, have much less sort of complete data than the kind of things that go into simple and the Ultracool sheet. But maybe it would be possible to, I think that might be an interesting thing to work on. Just an idea, though.
Wait,
Just a
Sean,
quick
could
question.
you?
What were the requirements on the Ultracool Dwarf sheet, Trent? Did they require to have that parallaxes or just Because if you have
Uh,
positions today, you have parallaxes, yeah? Or
no,
just
there's no
ignore
requirement.
that.
There's no requirements for what, I mean, you just, well, spectroscopically confirmed, ideally, but we do have lots of the interesting photometrically identified super late type objects. But we're not going to put a we're going to put a photometrically estimated late M dwarf in there, for example.
Yeah.
That's the only real requirement. Coordinates.
So how do you deal with the coordinates? You just ignore the fact you don't have proper motions and parallaxes when you talk about, when Mike was talking about today's, today's
Yeah, well, I mean,
coordinates.
not everything does, right? So it's just that if that information is available,
Okay.
then you can compute coordinates. But yeah, it's not required.
So I'm not quite sure how that differs from what you're after, John. If you're after everything within 100, ultra-cool dwarfs are going to be there, if I understand correctly what Trent is saying. What's missing from what Trent is saying?
Well, maybe, yeah, I just don't know. I mean, I sort of imagine that there could be there must be some list of candidates that perhaps becomes more and more marginal, and maybe doesn't rise to the level that that they can put, sort of the work in. I don't know. I mean, I'm just speculating, I guess.
I mean, is there a list of the ultra cool sheet rejects? Like the things that didn't quite rise to the level that, I don't know, need some follow-up?
Ooh, that's interesting. I mean, we don't really. That's suggesting. No, I would say like one of the big sets is like the things with SDSS spectra from Rocio's papers and stuff, where there's like thousands of things that are late M and early L, but that don't really have much other information. We have not bothered trying to
I guess
do all
maybe
the
I should ask,
wise
I mean, is there a whole set of like pan stars, like color only candidates that, one could imagine sort of drawing up that sort of maybe beyond the level, they're definitely outside of 25 parsecs, right? Maybe, I mean, is there a big like sort of sea of those objects that are already lurking out there? Or is that not the case?
Will might be the best person to say. I know another cutoff for the electrical sheet was Will's thesis sample, which was L0, right? So that late M dwarfs are highly incomplete, especially at larger distances. Will, are you there?
I am here. I think that, yeah, I mean, at some point, I know when I did my search, I had lots and lots and lots of candidates and I whittled down. And a lot of the reason you whittle things down in a search like that is, okay, feasibility for follow-up. I wanted a few hundred, not a few thousand, but back a couple steps in those searches, yes, I could come up with lots and lots of candidates. And I actually could do a much better job now because we really understand the pan-stars colors a lot better. So easy to generate a set like that.
Of course, I guess LSST data release 1 is a great way to generate the set.
It is, but if you want
question
something ahead of time that's real empirical data, then I think pan-stars would be the good stand-in for that.
Okay.
We're gonna get as well pretty soon, perhaps in a year's time, a Euclid kind of avalanche of ultra stuff.
Yeah.
Literally an avalanche.
That is
not whole
very
sky,
true.
but quite a big part of the sky. So
Wonderful. Well, then we're approaching 3 o'clock, and it does get to be a long day in front of the computer screen. So maybe we'll stop the recording here, and if anyone